back. Here's our lecture on chapter 12 of your textbook, and you're going to continue the previous lecture by about regression models. There are a couple of things that I have to emphasize. If you're watching this video, that's the first time you're watching it. This material is being covered in another video. So the first 20 slides of this chapter was covered earlier. So that's the new video, and I assume that you've already either watched the first 20 slides video or you have reviewed that. So if you haven't done so, please stop the record the video and just go back, watch the first video and come back, because the materials that are being covered today will be so much correlated with the previous materials. If there is nothing new, it's an addition to what has been covered. So in the previous video, I showed you how to run a regression line and find a regression line that defines defines how cost is related to number of passengers. And I want you to remember that the regression line we found was 1.57 plus 0.0407 times x. There are a couple of things you can understand based on this slide, and one of them is looking over this coefficient. Let me define what this coefficient is and what it means. It's called the marginal effect. Marginal effect. And it means if you add one passenger to your fleet, how much extra cost you will incur. For instance, it means the cost of having an extra passenger is, remember we have to multiply that by 1,000, it's $40.70. So every single customer, every additional customer on average would cost us $40.70. So in general, in economics, usually you want to price such that it is more than your marginal cost. So if you want to, for example, based on this model, decide how much cost you will have and how you should price it, you should price it more than its marginal value, which is $40.70. Another thing I want to emphasize is that this is called fixed effect. It might be fixed cost. For example, that is the cost of having an empty plane. So irrespective of having any passenger, that is the cost you have. That is the fixed cost amount. Some other notes is that if you want to predict an amount for values which is so much more or so much less than the range of your values, you cannot do it based on these models. For instance, if you want to predict how much cost you will have if you have 200 passengers, and let's say 200 passengers is here, you cannot do that because your range is from 60 to 100. You might be able to predict the average cost for 101, 102, but for 200 it's too much away from your range. And that's the same thing for smaller values. So if you want to, for example, predict how much cost you would have if you have 20 customers, you cannot have it. So I want you to write down this equation because we are going to use that. Y hat is equal to 1.57 plus 0.0407 times x. Okay. One of the things you must do when you're dealing with such models is looking at the residual values. It's very important to look over residual values, because if your residual values do not have some characteristics, then your models are not working. So that's vitally important for you to, after running your regression lines, look at the residual plots and see how things are going to work. And to remind you, residual is actually the difference between what you observe, that is actual y, for example, what is your actual cost, and what you predict for that y hat. This is called the residual. And that reflects the effect of regression line at any given point. And remember when I said for deterministic for non-deterministic cases, we have this beta 0 plus beta 1 x plus epsilon. So this is the error term that you want to predict. That's the difference of your reality and what you get from your model. Okay, so let's work on the residual analysis. So let me remind you, our regression line was, I think you just wrote it down. Let me write it down as well. It's y is equal to 1.57 plus 0.0407 x. Okay, so that is cost. This is number of passengers. So let's see how we can find the residuals. So this is our original data. This is our number of passengers. This is the actual cost, that is y, actual cost. So let's see what we predicted. So let's see what is our prediction for 61. In order to find the prediction for 61, you just replace it in the formula you have. So y at 61 would be 1.57 plus 0.0407 times 61. So if you just calculate it, the number you will get will be 4.053. So that is our prediction for 61, and you can see that here. So if you do the same thing for 63, your prediction will become 4,134, and so on and so forth. So you do it for every single observation you have. So the residual would be the difference between what you observed, y, and what you predict for that observation. So y minus y hat. So for first observation is 4.28 minus 4.053, and the difference is 0.227. So that means our prediction is $227 less than the actual cost for 61 passengers. Here it means our prediction is $54 less than the actual prediction is, sorry, $54 more than the actual cost, and so on and so forth. So that is the residual value. And if you add them up, you should always get 0. Here you don't get 0 because of roundup error, but if you just do it with more decimals, you always, if you sum them up, you always get 0. So these are our error terms. We are going to use every single one of them. You always have some positive and some negative numbers for sure. That is always happening. So let's look at it graphically and see what residual means. Residual is the vertical distance of this. This was y, and this is y hat. At this specific point, let's call it 77. This is y hat at this specific point, let's call it 86, and so on and so forth. So one thing you can do is to draw residual on x variables. For instance, here our observation is 62, and this is our positive residual. So at 62, this is 62. At 62, my residual was whatever it is here. It's 0.21. At 64, my residual is negative something. It's negative, let's say 0.5. And so on and so forth. So for every single observation we have, we can draw the residual on number of passengers. So you always draw residuals on x variable, your independent variable. There are a couple of rules that should be apparent on your residual graphs. And that is very important. That's something you should always remember. The first one is the errors should not show any, so let me write it down. Error plot or residual plot should not show any pattern. Any pattern. If it shows a pattern, that means your linear model is not useful. Any pattern. So fortunately, in this example, our residual plot doesn't show any pattern. You cannot find a line or a pattern that describes that. And another thing you can see is outliers based on this graph. Outliers are the observations that are far away from general. So that means they should have a large residual value. For example, if you had one observation, let's say here, one residual here, it would be so much away from our mean. Or we had an observation here, that would be so much away from our general graph. So we should, if you see large deviation from the origin, that is called outlier, and you should remove it from your data set and run your regression line again. Otherwise, your results are not reliable. So that's a very important topic. Please bear that in mind. So the residual, if your regression model is correct, you should have some very important characteristics. The first one is that you should not see any pattern in your residual plot. Here we see a nonlinear pattern in our residual plot. That means this is not acceptable for us. If you observe such a residual outcome, it's not acceptable. Your errors must have same variance around 0. Remember, the summation of all errors will become 0. That's why it's scattered around 0. Here in this graph, you had more errors at the beginning, less errors at the end, less variance of errors at the end. That means it doesn't have a constant variance around x. That's why it's not acceptable. Here we have low variance around 0 here, but we have large variance around 0 here. That means this is not acceptable either. There is one more case that is also not acceptable, and that is when let's say you have a model like this. Okay, so if you have a model like this, here you have large variance that becomes smaller, and then we have large variance at the tails. That is also not acceptable. So our residuals should be scattered around 0. They should show no pattern, and also they should show constant variance around 0. And the last one is your error terms should be normally distributed. That means if you just draw a histogram of your error, it should look like this. They will scatter around 0. These are the assumptions that should hold. Otherwise, your regression model is not useful. In your textbook, you have an example. You have another example on a number of full-time workers and number of beds in the hospital. Usually, when the number of beds in hospital is more, you will have more full-time workers because you need more nurses or full-time workers to take care of that business. So there is no doubt that it is positively correlated. And here is residual plot. So this is the original residual plot that you see. Let me use black. Okay. It is scattered randomly around 0. That is fine. So you don't see any pattern here. One thing that is striking is that you see less variance at the beginning, more variance at the end. That might be problematic. So let's look at the graph. Let's look at the residual histogram, it looks relatively normal, and I suggest we skip this part. That's another way to see if your probability is normal. If it's on this line, it's normal. It's not. So assume I haven't covered this part. So this is an okay residual plot, specifically because we have very few amount of observation. Do you remember what an observation would be called if the residual plot would give you a point like this? Do you know what this point would be? I think you guessed it. That is called the outlier. If that was here, it would be outlier. We should have just omitted it from our data and run our regression lines again. Here is another example. It's the production of carrots versus the production of sweet corn. I think they're highly correlated because it will show that if we had a good season or bad season, that's why they are correlated. If it's a good season, both of them will increase. If we have a bad season, both of them will decrease at the same time. You clearly see a problem here, and that is equal variance assumption that is being violated. It is scattered randomly around 0. That is fine, but when you look at the variance, scatterness of variance here, you see less variance at the beginning, more variance at the end. This is not acceptable for a linear model. The residual plot is almost okay. You see a normal distribution here. Of course, you have more tendency at larger values than the smaller one, but since you have a lot of data, you perhaps have more than 100 observations, maybe 200 observations, then you're not going to accept that. And by the way, if such a thing is observed in more advanced courses, you can just take care of that. You use weighted least squares that takes care of this problem, but that is beyond the scope of our talk. So now we understand how to define a scatter plot of errors. Now let's work on more statistics on errors, and it turns out that one of the important parts of residuals or errors is a standard error of that, a standard deviation of your error. That's a very useful measurement of error. Specifically, if you want to see, if you want to build up the confidence interval or construct confidence interval for your prediction, you need this value. So let's see how we can find the standard error. Standard error of estimate is denoted by SE, standard error of your estimates. That means standard deviation of the error of the regression model. So for the errors you have, the standard deviation of them is called SE. That's a very important measure. So let's see how we can compute it. It turns out it's very easy to find the standard error of standard deviation of error, which is called standard error. To do that, you need to use a notion called SSE. I urge you to just write this down because we are going to use this measurement a lot. SSE is sum square error. Remember when I defined SS in the class, I said whenever you have SS of a variable like this, that would become summation of the first variable minus its mean times the second variable minus its mean. And since these are the same variables, that would become summation of x minus x bar squared. Okay, so now let's work on sum square of errors. Sum square of errors would be summation of error. Error, we remember, was y minus y hat minus mean of error. Let me just write it, mean of error times itself, which is squared, but squared. But it turns out mean of error is equal to 0. That is why sum square error is summation of y minus y hat squared. That is SS error. And by the way, when you repeat same thing twice, you can just write it once. So that will be sum square x. Okay. So sum square error, where indeed sum square error, that's why we wrote it as SSE, will be summation of y minus y hat squared. That's a very important measurement that we are going to use over and over again in the course. If you just write, remember, and also remember y hat was b0 plus b1x. So if you do some math and just replace b0 plus b1x into y hat, and you can simplify that equation to this one. You usually need to use this formula. You usually use this formula. Anyhow, you need to find SSE. Once you find SSE, the square root of SSE divided by n minus 2 is called standard error. So one thing I want you to remember is we divided that by n minus 2. Why is the case? None of our business, but remember we have to divide it by n minus 2 to get. So many people forget that and divide it by n minus 1. It's wrong. We should divide it by n minus 2 and take a square root of that. So I want you to write down, stop the tape and write down this formula as well. SE is equal to the square root of SSE divided by n minus 2. And also write this down. SSE is sigma y minus y hat squared. Okay, so now I assume you've already did your homework and just wrote it on a piece of paper. So let's find the standard error for the airline data. I just want to remind you that SSE was summation of y minus y hat squared. In a couple of slides ago, I just showed you how to find y minus y hat, which was residual. We would just plug in these into our regression lines. We would get our predictions, actual observation minus predictions would give us this. So we just add one more column and just square our errors. So here 0.05153 is 0.227 squared, and negative 0.054 squared is this one, and so on and so forth. So we just squared our error terms. So in order to find SSE, we just sum these guys up. So this is the summation of whatever we have on top, and that is SSE, which is sum square error. How do we find SE, which is a standard error? Standard error was the square root of SSE divided by n minus 2. What was n? N was actually 12. We had 12 observations. So SSE would become a square root of 0.31434 divided by 10. So that will be our standard error of estimates. So in next slide we see that SE was calculated, and we found that SE is 0.1773. So that is the standard error of our estimates, and that was SSE. SSE is 0.13. So please record these values as well, right? Write down for The airline data SSE was 0.31. For airline data, standard error or SE was 0.1773. Please write it down because we are going to use these observations a lot, these values a lot. Okay, so let's get back to the outcomes of Excel. I told you earlier that Excel creates, if you just put data in, use Excel, it does provide some regression lines for you. And earlier I defined what these coefficients were and how you could use these coefficients to find the actual regression line. I taught you that a couple of slides ago in previous video. I remember back then I told you we don't care about what is the rest. So let me explain one more outcome in this slide, and that is S. So the S you find in Excel is actually SE. Okay, so it's 0.177. That's the same value you found earlier. Okay, so one of the other notions that is being used for seeing how good our model is doing, how good our regression line is called coefficient of determination. Coefficient of determination, and it's shown by R, capital R squared. So it's coefficient of determination, or R squared. The coefficient of determination, or R squared, measures how much variability of your data is captured by your model. Again, how much variability of your dependent variable was captured by your linear model. It's a value between 0 and 1, or 0% and 100%. And the closer it is to 1, the more of the variability is captured by a model. Okay, so if your R square is 100%, that means you had a completely linear model and all of your variability was captured by your model. If it's 0, that means your linear model is very poor in predicting reality. So this coefficient of determination changes from 0 to 1. And it's actually, for the case of you when you have only one y, for the simplest linear model, when you have b0 is b1x, R squared is actually R squared. So that is coefficient of correlation. This is called coefficient of determination. So this formula only works for simple linear regression when you only have one independent variable or one dependent variable. Okay, so if R, for example, if small r is 0.5, R squared would be 0.5 squared, which is 0.25, 25%. So let's see how we can find the coefficient of determination. Please do not panic by seeing what's going on later. Actually, again, everything is pretty straightforward. Just try to see what it is doing. So let me explain what it's doing. So we want to find the portion of data that is captured by the model. So in general, your initial error is SSYY. That means if you do not have any measure to predict y, you would always use y bar to predict it. For example, if you want to predict what is the grade, what is your grade in the class, and you do not know any other information about a specific person you want to predict it, your best guess, who might be your guess, is that person will get an average of the class. So your predictions for a random person is the average of the class. That's the best you can do. and that is SSYY. The variation in that prediction is SSYY, which was sigma of y minus y bar squared. So that is also called, in some literature, this is called sum squared total. That is the total variation exists in your model. So it has two parts. This total variation has some part that can be captured by your regression. That is called SSR. That is the part that can be captured. That's the part you can explain by your model. Plus some part that you cannot capture. That is sum square of your errors. These are the ones that are left. So SSY is SSR plus SSE. So R square is actually the ratio of what you were able to get from SSR, from your regression, divided by total regression existed. So if you just compare this part and this part, you will see that this is equal to 1 minus SSE divided by SSR, SSYY. So that is R square. So to show it more formally, SSY is total error that exists. That is, if you would predict y bar for every single observation. That is the worst you can do. Okay, so and at that part, if you just do the math, is sigma y squared minus sigma y squared divided by n. So that is the total variation exists in your model. It has two parts. The ones that you could explain by your linear model, by your regression line, and the one that you were not able to explain. That is the unexplained part. The explained part is called SSR. That is sum square of your regression model. SSE is the unexplained part. That is the sum square of your error. So if I divide both sides of this equation by SSYY, you would get 1 for here, right? This is 1. SSR divided by YYY plus SSE divided by YYY. And this guy is called R squared. This is wrong. This is capital R squared. In this specific case, when we only have one variable, it's also equal to R squared, but it's not generally the case. And it's also 1 minus SSE divided by SSY. So you should see which variables are given to you. Usually either SSE or SSR is given to you, and you can find the rest. I showed you how to find SSE in a couple of slides ago. That was sum square error, and I asked you to write that value down. I intentionally asked you to write it down because we were going to use that. And SSE in the previous example was 0.3134. 0.3134. So let's see what is R square in the case of our airline. So SSY, based on this formula, is sum y squared minus sum y squared divided by n. I've already shown you how to find sum y squared. So if you have some y's, you just square them, and the summation of everything you have here would be sum squared y squared. And the summation of everything you have here is summation of y. So I've already shown you how to do that. So based on our previous sections, we calculated SSE. So the only thing that is left is to find SSYY. I suggest you look over, let me check what page it was. Look over page 22. Page 22 of your lecture, and of course page, let me check, I need to look over my notes, and also page also page 18 of your lecture to see if you can find values sigma y squared and sigma y squared. So if you do the math and just plug in numbers, you get 3.11 for total amount of variation. So your r squared, which is only in this case is r squared, is 1 minus SSE divided by SSY. SSE was 0.33, SSY was 3.11. So your R squared is 8.99. That means 89.9% of the variability of the cost of flying is accounted by number of passengers. So that's a very strong model because you were able to capture 90% of its variability. So let's get back to the outcome of Excel. In outcome of Excel, we can now define another interesting variable and another interesting observation, and that is R squared. So R squared is 89.9%. It's given to you. So the software just takes care of that. That's very interesting. So now we turn our discussion into hypothesis test for slopes of the regression line. So let me motivate the talk this way. So y is beta 0 plus beta 1x. I have a question for you, and that is, when do you think our model is worthless? Is it when beta 0 is equal to 0 or beta 1 is equal to? When can't we use x to predict y? That's the time that our model is worthless. I think you guessed right. When beta 1 is equal to 0, irrespective of value of x, you always get y equal to beta 0, right? So if beta 1 is equal to 0, no matter what x is, you always get same value for y, and that will be beta 0. That's why it's vitally important to check if the value you get from your sample, which was B1, suggests that beta 1 is actually different from 0. So that is why we always run our hypothesis test. We always run our hypothesis test on population slope, and we want to see if it is significantly different from 0. So that's always what we are trying to do. So our hypothesis test is always on a slope of regression line, and we want to see if that is different from 0. Ideally, we want to reject the null hypothesis, because if we cannot reject the null hypothesis, that means we didn't have enough evidence to say beta 1 is not equal to 0, is different from 0. So 99% of time you're interested in a two-sided test that checks whether beta 1 is equal to 0 versus beta 1 is not equal to 0. And ideally, you want to reject your null hypothesis to say, okay, your model is significant. If you cannot reject your null hypothesis, it only means one thing, and it means your model is not significant. That means your linear model cannot be used in the context that you're trying to use it. So, we have to run it on the slope, and if we can find enough evidence against that being equal to 0, we are done. Otherwise, we cannot use our model. So, the hypothesis test tests that if the slope of the regression line is different from 0, and if it's different from 0, then x's can give predictability. So that's the only test that is important for us. If the slope is not different from 0, the regression line is doing nothing more than the average line of y predicting y. Remember, in rudimentary math, ideally we want to use x to predict y. But if we have this line is parallel to this line, this axis, and that is when y is equal to beta 0. That means irrespective of value of x, you always predict the same thing for y, and you predict this amount. So ideally you want to have beta 1 different from 0. To formally state our model, so let's focus on the left-hand side of our slide. You either want to check whether beta 1 is equal to 0 and compared with beta 1 is not equal to 0, or beta 1 equal to 0, beta 1 is more than 0, that's one-sided test, or beta 1 equal to 0 versus beta 1 less than 0. I would say 99.99% of time you're interested in the first two-sided test. That's why I will only focus on this type of test. Everything else is just the same as before. Nothing will change. The only thing that will change it would be your critical values, and I am sure you, based on the test hypothesis on mu, you already know how to deal with critical values. So if I teach you the two-sided test, which is the more cumbersome one, you will easily understand what the other things are. So the test statistic, T star, is B1 minus beta 1, which is beta 1 is 0 in our hypothesis test, but B1 is what you find from your model. So that is the coefficient or slope of your sample. Okay, and beta 1 is always equal to 0 in your case, because in our null hypothesis it is 0. So our test statistic is B1 divided by a standard error of B1. That is called standard error of B1. So B1 comes from your model. So let's see how we can find SP. SP would be the standard error of your model divided by the square root of SSXX. So let me remind you what was SSXX. SSXX or SS anything is just summation of that thing minus its mean times summation of the second thing minus the mean. Since they are the same thing, you just put the square on it. Or you can just simplify this and write it as summation of x squared minus summation of x squared divided by n, and this is our sample size. Okay, you already have all the values that you're looking after for your test statistic. So I want you to stop the tape now, look over slide 18. I am sure you have already opened that. That's slide 18. And also look over slide, let me find it in my notes. I want to see where you can find the values of interest. Look over slide 18 and also look over slide 22. Okay, look over slide 18 and slide 22 and also slide 29, 22, 18 and 29, and try to find T star yourself. Okay, try to find SSXX, SS standard error, and try to just find SB based on that, and then divide B1 by that. Remember our regression line was 1.57, so y hat was 1.57 plus 0.04 something. I think it was 0.047 407 x. So this one was our B1. So we know what B1 is. Please calculate SB. Put it there. You get the tested statistic, T star. So once we have the tested statistic, then we have to compare it with any significance level alpha %. And degrees of freedom n-2, we should find the T of critical value. So it's our T of critical value, we should look up our T table of two-sided with alpha % and degrees of freedom equal to n-2. Remember, n was 12, so n-2 will be 10. So please find the critical value as well. So if you do the math, and I'm sure you already did it, for alpha equal to 5%, that was a two-sided test, and we had degrees of freedom test 10, we find the T of 2.228. So everybody, please look up your tables and please try to locate it. If our T star, which is our tested statistic, is more than our critical value, this is called critical value, this is actually TC. If it's more than critical value, we reject A0. If it's not, we fail to reject our null hypothesis. Okay, so if it is, we reject our null hypothesis. Otherwise, we will fail to reject the null hypothesis. In this case, the T you will find, if you do the math, the T you should find should be 9.44. 9.44. Okay, the T you will find is 9.44. In this case, the boundaries of rejection zones, or TCs, are two-sided, and one side is 2.22. The other side is negative 2.22. And the T star we got was 9.44. Where is it? It's way beyond the rejection zone you have here. It's somewhere here, right? 9.44. So what is the general result you get from here? You reject your null hypothesis. Why? Because it's in our rejection zone. This is rejection zone. This is our rejection zone. And also this part is rejection zone. So 9.44 is clearly in rejection zone. So we have clear evidence to say beta 1 is indeed different from 0, and it means our model is significant. That means our model is useful. It has some predictability. And that's very admirable because we want that case. We want it to be predictable. Now let's get back to the Excel outcomes. Fortunately for us, when you work with Excel, SE of coefficients are given to you. That is actually standard. This is actually SB. And also the T statistic is given to you. And it's very easy to find. That is our tested statistic 9.4, the one that you've just calculated that. And it's a relatively easy way to find out. If you have the coefficient itself, this is actually B1. If you have the coefficient itself and you have the standard error of that, you just need to divide coefficient by standard error to get T statistic. So 0.407 divided by 0.004312. It's actually 9.44, the same value you found earlier. That is your tested statistic. And here you had the p-value for this tested statistic. So that's the p-value. It is definitely, so the p-value is very small. It's very close to 0, and it's actually 0 up to 3 decimals. That is definitely less than 5%. That's why you reject your null hypothesis. That means you have a significant model. You can do the same thing for intercept. An intercept's name in Excel is constant. That's intercept 1.5698. That is 1.57 for our model. You can do the same thing, but it's not important. Usually you should only focus on the standard errors of your slope to check if that is significant. Another interesting thing is R-square is given to you. 89.9% is given to you. Again, adjusted R-square is none of our business. Some other thing I want to discuss is that SSE, SSYY, and SSR is given to you. This is SSR. This is SSE. And this is SSYY. That is the total error we have. SST or SSYY. Again, we don't need these. I'm not going to cover these, and these are none of our business. So these are everything I want you to know. First, if I give you such an outcome, you should be able to write down the regression model. Second, for example, if I give you the coefficient and standard error, you should be able to find T. If I give you coefficient and T, you should be able to find SE. Or you can, if I give you two of them, you can find the rest. If I give you SSE, you should be able to find SSR and R-square. Remember, SST was SSE plus SSR. So if I give you two of these values, you can find the next one. And remember, R-square was SSR divided by SST. So if these values are given to you, you can easily find 89.9%. For example, R-square here could be found directly by dividing 2. This is not 1, this is actually 2. Okay, R-square is 2.798 divided by 3.11 is R-square. And if you do the math, you get the same result that you get here, 89.9%. Okay, so the Excel outcome is very handy because you can extract a lot of things from there. So the t-value calculated from the sample in our previous example falls in the rejection zone, and the p-value is relatively small. That's why we reject our null hypothesis, so we have enough evidence to say that our slope is not 0. It's different from 0. That means our regression line have some predictability. The last topic of this course and this lecture and this chapter is about estimation. How do we use our models to do predictions, and how can we build up confidence interval for predictions? For example, how can we be sure with 95% confidence that our result is between this and that? For example, our prediction for a cost of airline with 73 passengers is between, let's say, $4,200 and $4,400 with 95% confidence. How can we do that? That is in the estimation part. So if the regression function is a good model, you can use that to predict your dependent variable based on the independent variable you have. In the simple regression line, you just substitute x with the values that you want to predict it with, and you will be done. And that will be your prediction for that value of x. So let's work on an example. That was our regression model on our airline model. That was our prediction was 1.57 plus 0.0407x. So let's say we want to predict how much cost on average we will have if we have 73 passengers. So what you need to do is just to replace 73 for x. So y hat will be 1.57 plus 0.0407 times 73. So our prediction will be 4.5411, which is $4,541.10. So our predictions, our point estimate for our prediction, point estimate for 73 passengers is $4,541.10. But that is not enough. That is not enough. Why? Because we don't know how good our prediction is. We don't know the confidence interval. That's just a point estimate. If I say with 100% confidence, I am sure that my cost is between $0 and $100,000, you would laugh at me. So this point estimate doesn't mean anything unless we can construct a confidence interval for that observation, for that prediction, and that is how we do it. We have two cases. We built up confidence interval for two cases. The first case is when we want to estimate the mean of outcomes. So let me explain what we are trying to do. Let's say we want to build up a confidence interval for the mean cost of all flights that have 73 passengers. That means, let's say we have thousands of flights with 73 passengers. Now you want to predict what is the mean outcome of all 1,000 observations that you have and that have 73. For example, one of them had cost 5,000, another one has 4,000, another one 4,500. So you want to predict the mean outcome of every single one. It's not a singular one. You're not picking up one flight and you're trying to predict that. You're trying to predict it for every single airline, the average of every single airline that carries 73 passengers. So to build up a confidence interval, you have your prediction for 73. That is your prediction. I think in previous slide I showed you that we predict that on average for 73 we expect that $4,541.01 will be spent. So that's the average, plus minus T alpha over 2 and n minus 2. So let me explain what alpha is here. So alpha is actually 1 minus confidence level. So if your confidence level is, and that's the alpha two-sided, you should divide it by 2 to look it up in our table. So let's say confidence level was 95%. The alpha of two-sided would be 5%. So if you want to look up two-sided 5%, you should, with some degrees of freedom, then you should look at the two-sided case. And it should have n minus 2 degrees of freedom. We had 12 observations, so n minus 2 is 10. Time standard error. I showed you how to calculate that part. You already have that. Times a square root of 1 over n. N is number of observation. Here is 12. X0 is what you're trying to estimate the function for. That is 73 in this case. We want to predict it for 73 passengers. X bar is the average of your x variables. average of X. For our observations, we found that the average was 77.5. And SSXX, again, we used it earlier. You know how to deal with that. That is summation of X squared minus summation of X squared. And we have already calculated that many times. So let's build up a 95% confidence for the average of all flights that have 73 passengers by replacing numbers inside it. So I want you to look up your t-tables. Please look up your t-table with 10 degrees of freedom and try to find 95% of it. Remember, alpha is 1 minus CL percent of two-sided, so alpha 5%. So that will be, you should locate 2.228. Please locate this number. That is extremely important to find it out. Our prediction for 73 based on our previous slide was 4.5411. So that is okay. SE, I've already asked you to write it down. We already have that. Is 0.177. N is 12. We just replace it. X0, I showed you, is 73. X bar is the mean of our all accounts, is 77.5. SSXX, summation of X squared was 73,076. So this is this part. And summation of X squared would be 930 squared, and N is 12. So if you do the math, you would see that on average, you expect that for all of the flights that have 73 passengers, your average cost be between 4,400 and oh, I think that has a dot here, or even not here. Oh, it has dot here. The point is here, so it's 0.1220. I wish I knew how to erase that. Unfortunately, I don't. Yeah, I don't know how to do that. So, but it is 0.12220. So for all flights that carry 73 passengers, the average cost is between 4.4191 and 4,663. That's a very strong. That's a 95% confidence. With 95% confidence, you're sure that the average outcome is between these two numbers. And we can do our predictions for different values. We can do the same thing for 62 passengers, 68, 73, 85, and 90. So one thing I want you to notice is that the closer we get to 77.5, which was our prediction, which was our average of X, the closer you get to that, the smaller this interval. 62 is so far away from 77.5. That's why its confidence is 0.18. 68 is closer to 77.5. That's why this value decreased. 73 is even closer to 77.5. That's why it's decreased again. 85 is further away in comparison to 73. 85 is 7.5 units more than 77.5, but 73 is only 4.5 units less than that. That's why it started increasing. So that's always the case. The closer you're to the mean, the more sure you are about your prediction. So here we have another case. So we can build up a confidence interval. Now we want to pick only one airline. Let's say flight UA 270. That's only one airline, one flight, and we want to predict its cost there. Instead of predicting the average of all flights that have 73 customers, here we are only interested to know the cost of that specific flight. Usually when you want to predict one thing, you're less sure than when you want to predict for the average of everything. The formula for prediction is very close to the previous one. Same y hat, same t, same se, same 1 over n, and same x0 minus x bar squared as xx. The only thing that is different is this term 1. So the only thing that has changed, if you want to have a specific value of x, a specific flight, is that. So for example, if I want to estimate what would be the average grade of my Ch12 class section 8, I am very more precise than picking one student in my class and want to predict his or her grade. It's always easier to predict about the aggregate number of people instead of just one special person. So that's why we have an additional term, and that is what increases the confidence length, that is width. And so for your homework, please try to replicate this confidence interval and try to find these confidence levels for these values 62, 68, 73, 85, and 90. This time for individual, just try to calculate that. It's very, very helpful. Okay, here is our penultimate slide. It shows the confidence interval. Okay, so so we have black detached, black broken line here. That is the confidence interval for means of different groups. For example, here is 77.5. At 77.5, my 95% confidence is here. This is my prediction for 77.5. This is the upper limit of my prediction for 95% confidence. Here, this is my lower limit. If you go further away from the mean, our confidence interval will become larger and larger. So this is my confidence in 95% confidence interval for 77.5, which was our mean. The confidence interval for a large value like 98 is this much. It's significantly more than confidence level at 77.5, and so does for very small values like 60. This is significantly wider than what you observe in the mean. So that is for the mean. These orangish observation, this orangish confidence level, is a 95% confidence interval when you want to predict individual observations, individual flight with certain number of passengers. That's the individual one. Again, if you look at the prediction for 77.5, first of all, it's so much larger than the case that we were working on individual, right? The individual had this much confidence. The mean has this much confidence. The individual has this much confidence, the prediction. The point estimate is the same, but the confidence level is much more. And if you look at the tails of our graph, again we see that this confidence increases as you go further away from the mean, either this way or that way, it doesn't matter. If you go this way, again the confidence increases. So the confidence interval for the mean is always less than the confidence interval for individual, and that is shown in this picture. So that is confidence level, that is the personal confidence level. In another context, that is when you want to predict number of beds, when you want to predict number of full-time employees versus number of beds. Again, you see the same thing. The mean of our observations is around 50 something. That produces the smallest amount of confidence interval for mean. As you go further away from the mean, it starts increasing, both here and here. That's the same thing for when you want to predict something for individuals. In the middle, you have less confidence interval than at the tails. Okay, thank you for listening to this video. We are done with Chapter 12 lecture, and we are officially done with everything that was covered in the class. It was a pleasure teaching to you.